In this video, we're going to talk about how to handle limits where you have the power of 3 involved. So here we have the difference between two perfect cubes, and here we have the cube root of two terms. These are entirely different problems, and here's why. On the left, in green, we have the difference between two perfect cubes. X cubed is x cubed, and 2 cubed is 8. So here, if we had a cubed minus b cubed, we would be talking about x cubed minus 2 cubed. So in this scenario, a would equal x and b would equal 2. Now, there are there are identities for the difference between two perfect cubes and the sum of two perfect cubes. So I'd like to review those quickly. The difference between two perfect cubes consists of a setup and a trinomial. Okay, a setup and a trinomial. Okay, the setup always has the same sign as the difference between the cubes. So here you see a negative, that's a negative. So I'm going to put S here for same. The first sign in the trinomial is opposite to what is in the setup. So this is going to be opposite. The second sign in the trinomial is always positive. Always positive. So the way I remember this, ladies and gentlemen, is SOAP. Same in the setup, opposite is the first sign, and always positive. SOAP, S-O-A-P. Now, in the setup, you just put a minus b. The first term in the trinomial is a squared. The second term in the trinomial is ab. And the third term in the trinomial is b squared. Now, let me prove to you that SOAP works. Just beneath it, I'm going to do the sum of cubes, perfect cubes. Whether it's the sum or the difference of cubes, you have a setup and a trinomial. The first sign in the setup is the same as in the opposite side of the equation. The first sign in the trinomial is opposite, and the final sign is always positive. Here we go. A plus b, a squared, a times b, b squared. Same, opposite, always positive. I suggest you take a screenshot of this, folks. Let's now proceed to solve the limit on the left, where we do have the difference between two perfect cubes. First thing, whenever you have a limit, you always try to plug in. See if you can do that. Immediately we find if we plug in 2 for x, we're going to have 0 in the denominator, which means our next move is try some algebraic manipulation to see if we can cancel. We have the difference between two perfect cubes in the numerator. That's going to be our setup times our trinomial difference between two perfect cubes equals a setup times a trinomial. Lo and behold, we can cross out the x minus 2. This now is amenable to plugging in. This becomes 4 plus 4 plus 4, and your limit is going to be 12. Okay, can't do that here. Totally different problem. So let's talk about how we're going to handle this blue limit. The first thing that you want to notice is we are not dealing with different subperfect cubes, but the cubed root is involved. All right? That means we are still going to use that identity of the difference between two perfect cubes. So let me remind you what that consists of. If we have a cubed minus b cubed, we have a minus b. I'm not going to write it out, times a trinomial. We have the setup. We have the difference of cubes. And the difference of cubes equals the setup times the trinomial. Now, whenever you see 3 here, the cubed root, otherwise known as a fractional exponent of 1/3, ladies and gentlemen, that is the setup. This is the A, and this is the B. And we're going to use that to our advantage. Because look at this. This is our setup. Right there. We're going to use this setup, and we're going to work backwards. Or I should say, we're going to work to the right, and we're going to find that trinomial using the setup. And then we're going to go to the left, and we're going to find the difference of cubes using the setup. Let's talk about how to go backwards here. Here's our setup. Our difference of two perfect cubes would be each of these terms cubed. Our trinomial, I'm never going to be able to fit this. Our trinomial is going to be this squared plus a times b plus b squared. Okay, here's your setup. Here's your trinomial. And here's your cubes. Okay. Ladies and gentlemen, we are going to take this original limit right there, and we're going to multiply it top and bottom by the trinomial. That's our next move. So we're going to come here, and we're going to multiply by trinomial over trinomial. Okay, let me clean this up and come back in 2 seconds. Okay, to review, this limit did not give us perfect cubes. This limit gave us the setup. Okay, I just rewrote this as fractional exponents. Using the setup, we created the difference between two perfect cubes. All we did was cube a and b. We also took the setup and created our trinomial. Our plan now is to multiply the top and bottom by the trinomial after we simplify what we have. Okay, on the left, we apply the power rule. 3 times 1/3 gives us x plus h. 3 times 1/3 gives us x. Look how beautiful that is. Because now x plus h minus x just gives us h. Okay? Now, the setup is going to stay the same. Can't do anything there. Moving to the trinomial, we're going to apply the power rule, and we're going to have x plus h to the 2/3 power plus x plus h x to the 1/3 plus x to the 2/3. Okay, now here is the whole crux of this technique. Folks, if we come along and we multiply the setup times the trinomial, what do we get? The setup times the trinomial. Here it is. The setup times the trinomial equals this. And what does this equal? H. So on the top here, we're going to have H. On the bottom, we're going to have H times the trinomial. And look at those H's, they cancel out. So our limit is going to be 1 over the trinomial. So all we have to do now is take the limit as h approaches 0 of 1 over the trinomial. Let's do that. Let's plug in h equals 0 to the trinomial, and that'll be our denominator. We have 1 over x plus 0 squared plus x times x to the 3rd. Sorry, there should be a 1/3 here. Plus x to the 1/3, because h is 0, times x to the 1/3 plus x to the 2/3. That's going to simplify to 1 over x to the 2/3 plus, here we're multiplying, we keep the base the same and we add the exponents. Equals 1 over 3x to the 2/3, and that is your final answer. In case you have a teacher that won't let you have a fractional exponent in the denominator, we can rationalize that. The goal is to try to get x to the 1st power. So what are we going to do? We're going to multiply top and bottom by something that's going to get x to the 1st power. X to the 1st power is the same as x to the 3/3. So we're going to have x to the 1/3 on top. This is going to, we multiply that, we're going to get x to the 3/3. So we're going to have 3x on the bottom. And if you'd rather have the radical form, that is the final answer for that limit. Okay, folks, if you're like me, you will find that previous method that we use very cumbersome. So let me show you another way to do this using U substitution. This is not the difference between perfect cubes, so we cannot use our identity. But what we can do is let U equal x plus h to the 1/3 power. Okay, all I'm doing is letting u equal this term, which when written in fractional exponent form would give you what we have in yellow. Now what I'm going to do is I'm going to raise both sides to the 3rd power. And I'm going to get u cubed equals x plus h. I'm going to take away the parentheses because I don't need them. And I'm going to solve for both x and h. So I'm going to get x equals u cubed minus h. And I'm going to get h equals u cubed minus x. The idea is I'm now going to use these entities to substitute into the original limit. Okay, let me make some room, show you how we do that. First thing we need to do is we need to change the limit as h goes to 0 and get u involved. In other words, our new limit is going to involve what's happening with u. Okay, u. Here, h was the star of the show. In the new red limit, u is going to be the star of the show using these substitutions. So the first thing we need to do is we need to say to ourselves, what's happening with u as h goes to 0? So let's come over here and see what's going on. As our original substitution, which I inconveniently removed, was this. I apologize. So as h goes to 0, if I plug in h for 0, what happens to u? U approaches x to the 1/3 power. So we're going to use that in our new limit. Okay, let me repeat that. Using this here, as h goes to 0, I took that and I plugged in 0 for h, and I was left with u approaching x to the 1/3 power. So that's going to be the new limit we're going to use. Okay. Now, let's continue our substitution. X plus h to the 1/3 power. X plus h to the 1/3 power, that becomes u. Minus x to the 1/3. Let's see, we have x equals this, but I'm going to leave that as x to the 1/3. And now, for h, I'm going to put, for h, I'm going to substitute in u cubed minus x. Now, here's the big part of this. Folks, this is the difference between two perfect cubes. Our a and b are going to be a is going to equal u, and our b is going to equal x to the 1/3. You see how x to the 1/3 cubed gives you x, u cubed gives you u to the 3rd power. Now we're going to build our trinomial. We're going to have u squared plus u times x to the 1/3 plus x to the 1/3 squared, which is x to the 2/3. Okay, so I'm going to replace what we have in the denominator here with this identity in our denominator right there. And what do you notice about the numerator and the denominator? They cancel. So now, folks, all we need to do is plug in u equals x to the 1/3 right in here. So we have 1 over u squared, which is x to the 1/3 squared, which is x to the 2/3, plus x to the 1/3 times x to the 1/3. You recall from the previous portion of this video, that is x to the 2/3 plus x to the 2/3. So this same limit equals 1 to the 3x to the 2/3, which is the same result we got using the previous technique. Let's now look at this limit and notice that we have x to the 1/3 power, but down below, this is a hidden version of the difference between two perfect cubes. Here we go. This is really x to the 1/3 cubed minus 4 cubed. So using that information, we know that our a equals x to the 1/3 and our b equals 4. So we can put our setup as and our trinomial as x to the 1/3 squared, which is x to the 2/3, plus 4x to the 1/3 plus 4 squared. And look what happens. These cancel. We now have a situation where we can plug in 64 into x and x. 64 to the 2/3 power. The way I remember it is the root is beneath the ground. So if you envision that fraction line as being the ground in a garden, the roots would be underground. So that's our root. Cube root of 64 is 4. 4 squared is 16. Here we have 4 times the cube root of, I'm sorry, that's 16. 4 times the cube root of 64 is going to be 16 plus 16. This limit is going to be 1 over 48. So the lesson here is recognizing that that is a hidden difference between two perfect cubes. This next limit, again, you always try to plug in. We can't do it. We get 0 in the denominator. We are dealing with a 1/3 root up here, but this is another example of a hidden difference of two perfect cubes. So folks, whenever you see 8, whenever you see 64, think about difference of two perfect cubes that are hidden. Now, one thing I want to point out is that if you multiply by the conjugate here, okay, remember the conjugate is just replacing the same two terms, but with a opposite sign in between. If you did that here, this is not helpful. You cannot use the conjugate when you are dealing with cube roots. And here's why. You can only use the conjugate when you're dealing with square roots. Okay, forget the denominator. Let's just look at the numerator. So if you want to multiply by the conjugate here, you're counting on the fact that this radical times that radical gets rid of the radical sign. And the reason is when you multiply the square root of x times the square root of x, since these indices are the same, those roots are the same, you are allowed to keep that same index too and just multiply the radicands. So the radicand here is x times x is x squared. Whenever the root of the radical matches the exponent in the radicand, you are allowed to simply remove this radical and the exponents, and you get the original radicand. However, if you were to try to do that dealing with cubed roots, this is what would transpire. You would have cube root of x times cube root of x. Because these roots are the same, you're allowed to keep the root the same and multiply the two radicands, and you would get x squared. Here, the root does not match the exponent in the radicand, so you are not allowed to remove that radical. You can rewrite this as x to the 2/3, but that is not helpful. So let's talk about how to solve this original limit in green. Folks, the important thing is to recognize that this is the difference between two perfect cubes. So this is really x to the 1/3 cubed minus 2 cubed. So here's our a, here's our b. So this is really a minus b times a squared, x to the 1/3 squared is x to the 2/3, plus a times b, plus b squared. Now, when you rewrite this as a fractional exponent, these go away, and you just plug in 8 into here, and you will end up with a limit of 1/12. Again, recognizing this is the difference of two perfect cubes. You might see x minus 125. That's a perfect cube. This is the difference between x and a third minus 5 cubed.